Okay, now the next one that we are going to look at is cycloalkenes. So cycloalkenes contains carbon to carbon double bond in the ring. We have like cyclopropene because there are 3 carbon. We have cyclobutene, there are 4 carbon. We have cyclopentene and cyclohexene. So nomenclature of cycloalkenes is similar to that of alkenes and similar for carbon atoms and the double bond are signated as carbon 1 and 2. So any carbon, look at it, this is a carbon with a double bond, so they are signated, they are usually given carbon 1 and 2. So we have, like, for example, this one, we have, because it's at carbon 1, if you see the 1, 2, so it's this at this carbon 1 that we have methyl, but the word cyclo must be added in naming them. So we have 1 methyl, 1 methyl cyclohexane, and this one we also have at carbon 1, 2, 3, 4, 5. So at carbon 1 we have methyl, and at carbon 5 we also have methyl. So that is why this one is named as 1,5-dimethyl cyclopentane, because we have substituent at position 1 and 5. Then the next one is the nomenclature of cis and trans isomers. So how do you know that this is a trans and this is a cis? Trans means transverse. You see, this one CH3 here is transverse to this CH2, CH3 is transverse. You see, why is that they are transverse? Look at it, they are transverse to one another. Look at it, this one is transverse and this one is also, look at it, so they are transverse. That is why they are called trans 2-pentene. It's trans 2-pentene because if you number the carbon, we have 1, we have 2 here, we have 3, then we have 4 here, 4, we have 4 here, then we have 5. So that is why it is trans 2-pentene, because it is transverse. And this one, look at it, is they are all the carbon that are attached to the double bond, they are in the same site. That is why they are cis. They are cis. If you number them 1, 2, 3, 4, 5, so you see that you have cis 2-pentene. Cis 2-pentene because it is at carbon 2, the double bond. So it's cis 2-pentene. So this is how you recognize them. You see that the ethyl group here attached to the carbon bearing the double bond are in the same site with the methyl, which is CH3. So cis, that is 2 particular atoms are adjacent to each other. You see they are adjacent. This one is adjacent to this one. And trans, the 2 atoms or group of atoms are across from each other. You see they are across. This one is across to this one. So that is why they are considered as a trans and cis. Then the next thing is the physical properties of alkenes. The physical properties of alkenes includes the boiling points and densities. So most physical properties of alkenes are similar to those in alkenes. Examples, the boiling point of 1-butene, cis-2-butene, and trans-2-butene and N-butene are close to 0 degrees centigrade. So you see N-butene, cis-2-butene, trans-2-butene, and 1-butene have almost the same boiling point with the normal butene because they have similar, their properties are almost the same. So the densities of alkenes generally is ranging between 0.6 to 0.7 gram per cm cube. Then the boiling point of alkenes increase smoothly with molecular weight. So it means that the more the number of carbon in the alkenes, the more the boiling point. And then increasing branching leads to greater volatility and lower boiling point. So it means that if you have a long chain hydrocarbon, then the more the branch that are attached to that long hydrocarbon chain, then the lower the boiling point that it is. Assuming now we have, let's say, we have butene, we have, let's say, pentene, and then we have, let's say, 2-methyl butene, and then we have 2,2-dimethyl propene. So you see that the number of carbon are the same, but the branching in 2,2-dimethyl butene are higher than that of 2-methyl butene and the normal butene. You will see that the boiling point of the 2,2-dimethyl propane will be lower because of the increasing in the branch or the substituent. So we should also understand this and put it in our memory that the more the branching, the more the lower the boiling point and the greater the volatility of the compounds. So polarity, they are relatively non-polar, as they are insoluble in water, but they are soluble in organic solvents such as zinc, gasoline, halogenated solvents. So they are soluble here, and they are slightly more polar than alkenes because electrons in the pi bond is more polarizable, contributing to instantaneous dipole moment. So actually, they are non-polar, but their polarity is slightly higher than that of the alkenes, and this is because of the presence of the pi bond. You know that, remember I told you, whenever you have a pi bond, it means that one of the electrons is, whenever you have a double bond, one of the electrons is pi bond and the other one is sigma bond. So because of the presence of that pi bond, that is why it is slightly soluble. So it is slightly more polar than that of this thing. Another thing, the vinylic bond tends to be slightly polar, contributing to a permanent dipole moment. Okay. And then the next thing is alkyl group are electrons donating toward double bond, helping to stabilize it. So these donating slightly polarize the vinylic bond with smaller partial positive charge on the alkyl group and a small negative charge on the double bond carbon atom. So for example, propene has a small dipole moment of 0.35. So we should understand this. It means that when you have alkyl group attached to the double bond, so it helps in stabilizing and polarizing the compounds. And then the next thing is cis disubstituted alkene. This is a cis disubstituted alkenes. The vector sum of the two dipole moment is directed perpendicular to the double bond. So we should know this. I think, okay. So the next thing that we are going to look at is the preparation of alkenes. Preparation of alkenes.